Hello friends, welcome back. In our discussion regarding transistor, today we will see more about the bipolar junction transistor. As I had mentioned in the previous video, we chose bipolar junction transistor because it is more closer to the discussion that we had regarding PN junction. So it will be easier for you to understand the basic concepts of bipolar junction transistor. In today's video, we will see the various current components in the bipolar junction transistor, and we will be making use of the concepts of band diagram to understand more about BJT. Let us start from where we had stopped in our previous video. Consider the NPN transistor. We know two PN junctions are combined to form the NPN transistor. We have two junctions for the BJT, a junction formed between N and P and another junction formed between P and N. And at equilibrium, we know we have a constant Fermi level, and the band diagram will be of this fashion. The first NP junction, we have a band like this, and the PN junction we have the band like this. So this is the band diagram of a NPN transistor at equilibrium. We have a constant Fermi level, which is a straight line. And if we demark in the band diagram, this is the emitter, this is the base, and this is the collector. Now, in order to make the transistor work as an amplifier, we give biasing. And at emitter base junction, we give a forward biasing. The forward biasing is applied at emitter base junction. The negative of the battery is connected to the N type and the positive is connected to the P type. Along with this, we need to reverse bias the collector base junction. For that, we give another battery source. This is one type of biasing the transistor. You might have seen different types of biasing. This is one type. We are not going into the different types of biasing, but the basic requirement for a transistor to act as an amplifier is that the emitter base junction should be forward biased, and collector base junction should be reverse biased. This will make a change in the energy band diagram. Now the energy band diagram will look like this. Without the Fermi level, I am going to draw. At forward bias, we have a smaller potential barrier, and at reverse bias we have a higher potential barrier, because you know, on reverse biasing the depletion region increases. So if we demark the area in the energy band diagram, we have like this. And the electrons which is moving from the emitter reaches the base, and as you know, at base we are having majority holes. There is a possibility for recombination here. Whatever electrons that moves from emitter can recombine at the base, and the electrons which is remaining after recombination reaches the PN junction nearer to the collector, which is swept or attracted towards the lead connected to the collector, which is constituting the collector current. If we strictly see into both the carriers, we can say that the electrons moving in direction will constitute a current IE due to electrons. By convention, the direction of the current will be opposite to the movement of the electrons. Similarly, the holes from the base will move to the emitter, which constitute another current IEP, which is the emitter current due to the holes, IEP, which is in this direction. And in order to facilitate the recombination, we inject a base current IB. IB can be, this current is instrumental for the recombination. So in a generic expression or in a general term, the IB is constituted by both the emitter current due to holes and the base recovery current. This is regarding the first junction, which is the junction between emitter and base. Since the junction at or between collector and base is reverse biased, there will be only a possibility of a leakage current through the junction, which we can term as IBREV, which is the reverse leakage current. Ideally, this current should be very minimum, which can be neglected. If it is very minimum, this can be neglected. So the collector current, the main constituent is the emitter current due to the electrons. Because of that, we can rename it as INC. So the main components, main current components are IEN, which is the emitter current due to electrons, IEP, emitter current due to holes, IBREC, which is the current injected to the base, and IB reverse. This is a reverse leakage current and the collector current. If we remember the 2-point system A and B, and the third node C, which controls the current through A and B. A forms the emitter connection, B forms the collector connection, and C is the base connection. Now, after finding these current components, we will also try to define few factors, which is very important in the case of our discussion on BJT. The first factor is the base transport factor. Base transport factor, which is denoted by the letter B. Second one is the emitter injection efficiency. Emitter injection efficiency, which is denoted by gamma E. It's gamma E. Another factor is the current transfer ratio. Current transfer ratio, which we have seen earlier too, maybe in your basic course, which is denoted by alpha. And finally, gain of the amplifier, beta. Just remember the band diagram of the biased Npn transistor. I am redrawing it. The forward bias at the emitter base junction and the reverse bias at the collector base junction, and also the current components we know. We have IEN, IEP, IB recovery or recombination, IB recombination, IB reverse, and the collector current INC. The base transport factor B is given by INC by IEN. As I had mentioned earlier, the IEP, the emitter current due to holes, is not contributing to the collector current. So the base transfer function is the factor which gives us the idea about the factor by which the electrons moving to the base further moves to collector without recombination at the base. So we want this to be approximately equal to 1, which means there should be very minimum recombination happening at the base, or in other words, whatever electrons move from emitter to base should reach the collector. So ideally there should be very minimum recombination at the base. The base transport factor gives us the idea about how much electrons move to the collector. Next one is the emitter injection efficiency, as again mentioned, the total emitter current will be IEN plus IEP, and the emitter injection efficiency is denoted by out of the total how much emitter current contributes to the collector current. This also ideally should be equal to 1, which means the emitter current, the majority contribution of the emitter current should be due to the electrons moving from emitter to base rather than holes moving from base to emitter. The current transfer ratio alpha is given by IC by IE. We know the IC is INC. We multiply and divide by IEN, which is the emitter current due to the movement of electrons from emitter to base, so that the equation IC by IE can be rewritten as INC by IEN into IEN by IE. This term is B and this term is gamma E. So in other words, we could say that current transfer ratio is the product of base transport factor B and emitter injection efficiency gamma E. So B gamma E is equal to alpha. As we had mentioned earlier, B and gamma E is approximately equal to 1. So this alpha also becomes approximately equal to 1 or nearer to 1. Ideally, it should be like that. Now, the remaining term is the gain beta. The gain of any device is the ratio between output and input. Here the output is the collector current and we are controlling the collector current using the base current. So beta is IC by IB. Since here the IC is INC, we have written INC by IB. From our first year class, we know that alpha is equal to IC by IE. Also we know IE is equal to IC plus IB. Using this understanding, we can write IC by IB as IC by IE minus IC, which is equal to, by rearranging we can write IE by IC minus IC by IC, which gives it as 1 by alpha minus 1. Rearranging this, we'll get alpha by 1 minus alpha. This is equal to beta, or in other words, beta is equal to alpha by 1 minus alpha. The ideal term value of alpha is 0.99 or nearer to 1. So this becomes 0.99 divided by 0.01, which gives us the value 99, which is a high value. So in ideal case, the gain of the amplifier will be high. In order to make the gain of the amplifier high, we need a lower IB, or the recombination current. The IB is the base current, should be smaller. If it is smaller, we will have a higher base current, which is that if the base current is smaller, which means IEP plus IB recombination is smaller, then the gain beta will be high. In the NPN transistor, during our previous discussion, we had seen the requirement of having a smaller base current in order to get maximum gain. On the formation of the junctions and application of the biasing, since the emitter base junction is forward biased, we have a smaller depletion region at that junction, but there will be a still more higher depletion region at the another junction because it is reverse biased. Due to this depletion region, the effective base width has shrunk to this small area. Originally, the base width was this, which is the metallurgical base width. Due to the biasing, we have depletion region forming at the junction, a change in depletion region at the junction, which shrinks the base width to the smaller width, which is the neutral base width, known as the neutral base width. Ideologically, if we reduce the base width, the chances of recombination also reduces. We need the recombination to be minimum at the base. Only if that is minimum, we will have all the electrons moving to the base moves to the collector and contributes to our output current IC. So our requirement is to minimize the base width. So that is one technique by which we can improve the working of the transistor. Another thing is, we know, I will take another page. In an NPN transistor, this is the emitter, base and collector. Emitter is N-type, base is P-type, and collector is another N-type. The doping will be, in order to make it N-type, we'll have donors. But the doping at emitter and the collector can be of a different concentration. So we will say the doping at emitter as NED and here NCD. For the base, in order to make it a p-type, we have acceptors, impurities. Following the same nomenclature, we will have NBA. Now, just considering a PN junction, say the junction between emitter and base, which is forward biased. Due to the forward bias, electron moving from emitter to base can be given by the equation. Remember the previous discussions on PN junction. The current can be given by, the current density can be given by Q dN by Ln Ni square by Na, which is the whole concentration at P, into e raised to Q Va by Kt minus 1. Similarly, current due to holes moving from P to N can be given by Q dP by Lp Ni square by Nd e raised to Q Va by Kt minus 1. In our earlier discussion, we had seen the emitter current is constituted by the current due to electrons from emitter to base and also holes from base to electron. So this is the sum of these two currents, and we see Na is at the denominator here. Nd is at the denominator. If Nd is 10 raised to 18 and Na is 10 raised to 15, which means the emitter is heavily doped. More impurities are added and the base is lightly doped, so that this term will be more. We need this term to be more when compared to this term. So by adjusting the doping concentration at the emitter and base, we can control the transistor action as per our requirement. Our requirement is the collector current should be almost same as the emitter current, and the base current should be very low in order to get a higher gain. For that, we'll have a narrow base when compared to emitter and collector, and the doping also is different. We have a lightly doped base, lightly doped when in comparison with the emitter. So in construction, we have emitter heavily doped, base lightly doped, and collector moderately doped. And also in the construction, we have a longer emitter, a narrow base, and a collector. Emitter, base collector. So this discussion on the BJT gives us the concepts why the doping is different in case of emitter, base and collector, and also why the size of the emitter, base, collector is varied. This is required for improving the transistor action, which is to get more gain